let's start group theory. The algebraic structure that we want to study is called a group. Groups are very closely related to the concept of symmetry. In particular, if you take the set of symmetries of some geometric shape, they form a group, we shall see. And I want to study one of those examples in detail for motivation. So here is an example of what is going to turn out to be a group. Group of symmetries of a square S. So let's just take like a square in the plane with the axis along the coordinate axis and the center at the center. This is my S, this square. You can think of a square piece of paper if you want. But idealized, of course. So then, what do I mean by a symmetry of the square? A symmetry of the square S means a transformation that leaves S invariant. Now that sentence is rather imprecise. What kind of transformation? We'll give the examples, but I mean, let's say, transformations of the plane. So let's just say transformations of the plane generated by reflections and rotations of the plane. So that's a transformation of the plane that leave S invariant. Invariant means unchanged, exactly unchanged. So it's still not quite precise. It's better to give an example. So here's the square. What kind of transformation can I do to this square piece of paper that would leave it exactly like this? Well, I could take this, imagine a line through the middle along the x-axis and reflect it. And then the square would again go to exactly the same place. I haven't even, from the picture, I can't even tell that I did anything to it. So to mark that I did something to the square, I'll put a little arrow here to tell the difference. When I flip, the arrow becomes a downward arrow down there. Okay, so this is an example of a symmetry. This transformation. This, let's call it F for flip, F1. So this is reflection across x-axis. And this transformation does qualify as a symmetry of S. Reflection across the x-axis is a function from the plane to the plane. What function is it? F1 is really a function from R2 to R2. If I write an element of R2 as a column vector xy, F1 is a function that takes xy to x minus y, you see? Here is xy, and when I apply this reflection, it goes to x minus y. The x coordinate stays the same, the y coordinate flips. If you wish, you can represent this function by a 2 by 2 matrix, this 2 by 2 matrix. What I mean is applying the transformation to a vector is same as multiplying by this matrix on the left. Okay. So that's an example of a symmetry of S. Once we have figured that out, I could write down all the symmetries. You could reflect the square, across the y-axis. That would change like this. Let's draw the mirror. Flip across this line. Or you could flip it across the two diagonals. Let's draw this quickly. You could flip it across this diagonal, or you could flip it across that diagonal. If you do the first one, this arrow becomes that arrow. If you flip it like this, it becomes like that. Right? So this is, let's call this, just want to call this one F2, call this one F3, this one F4, something like that. So there are these 4 reflections. What else can you do? Well, you could rotate a square, right? You can take a square, our S, and rotate it around the center by 90 degrees. So if you rotate, then it goes like that. This is 90-degree rotation. Or you could rotate by 180 degrees. Turn it 180 degrees. Or you could take this piece of paper and turn it by 270 degrees anti-clockwise, which means 90-degree clockwise. They amount to doing the same thing. 270 degrees. Or you could turn 360 degrees, which amounts to doing nothing at all, because turning 360 degree in the plane brings every point of the plane back to where they started from. So we'll call this one R1, 90-degree rotation anti-clockwise. This R2, that's a 180-degree rotation. R3 is 270-degree rotation. And this is 360-degree rotation. I'll call that E. That's the standard name for identity, or identity transformation. Because if you think of these as functions, 360-degree rotation is same as the function that takes xy to xy. So E of xy is xy. Okay. Then I claim that these are the only what are called linear transformations that you can do to the square that would keep the square invariant. Well, if I give you these transformations that takes the square to itself, you could presumably cook up some new transformations by applying them back to back. See, you could take this square and apply, let's say, F1 first. Apply F1, then apply F2. Then reflect like that. So if I apply them back to back, the net result is also a transformation that leaves the square in its own place. I claim that this net result is again one of these 8 transformations that we have listed. Let's figure out. The best way to figure that out is quickly, if you're not good at visualizing these things, I'm not, just level the vertices and see what happens to the vertices. Let's level the corners 1, 2, 3, 4. After you apply this flip F1, what happens? The vertex 1 goes down here, the vertex 4 goes up, and same with 2 and 3, they get flipped over. 3, 2. And then when you flip across the y-axis, the 1 and 2 gets flipped, and the 3 and 4 gets flipped. So now let's see what happened as you went all the way. Oops. I'm sorry, that was not my F2, was it? My F2 was the diagonal flip. So this one, if you see up here, that was F2. So if you apply that diagonal flip, then 4 stays in its place, 2 stays in its place, and 1 and 3 get flipped. 1 goes here, 3 goes here. Now let's see the net result. What happened? Well, 1 turned anti-clockwise 90 degrees. Same for 2, same for 3, and same for 4. And I claim that if you visualize what goes on, or if you multiply the corresponding matrices, you'll see that this amounts to a 90-degree rotation. Anti-clockwise rotation. What we called R1. So the net result of applying F1 and then F2 is R1. So we say, or in other words, what we are saying is that applying the function F1 and then applying the function F2 to some point in the plane is same as applying the function R1. So F2 times F1 is R1. So this composition in this case, this applying these transformations back to back, turns out to be a binary operation on this set of 8 transformations. And let's call this set of 8 transformations D4. That's the standard name for it. Identity R1, R2, R3, and then F1, F2, F3, F4. What I'm saying is that if you take any 2 of these and apply them back to back, then you again get one of these 8. So this defines sort of a multiplication or a composition law on this set. And this composition law satisfies certain properties when you abstract them out on an arbitrary set. An arbitrary set with such a composition law forms a group. So this will be an example of a group. So it's a bunch of transformations that's closed under composition in this way, satisfying certain properties. We'll try to see what those properties should be when we play with this example a little more. I want to refer you to this YouTube channel called 3 Blue, 1 Brown channel on YouTube. It has a introduction to group theory video. Maybe I'll write down the link, what the title is, when I put the notes up. It's a wonderful introduction to the same thing. He actually walks through the same example, but he has beautiful animation showing the transformations. So I really, really very highly recommend. So before you go to the next video, maybe you can look through that. Or after you finish today's videos. You definitely consider that one of the reading exercises.